Hello, chemists. All right, this lecture is going to combine all of those combinations. So we're going to do electron configurations, we're going to do orbital diagrams, and we are going to include the quantum numbers. So this is the tie together to put all of those subjects into, if you will, one pot. All right, so if this one doesn't make sense, you of course can go back and watch, each of the middle ones, but this will be hopefully conclusive to all of those other pieces. All right, let's see, get rid of me and let's go to the whiteboard. All right, so we have played with electron configurations, orbital diagrams, and quantum numbers. And so it doesn't matter where we start, but I'm going to start with the electron configurations, and then I will tie it together, starting with those. All right, so we have electron configurations, we have orbital diagrams, and we have quantum numbers. All right, let's just do, let me see, looking at my periodic table. You know what, let's do carbon. All right, for electron configuration, the last noble gas that was full is helium. And then I'm in shell 2, and I am in the first two columns, which is shape S. And there's 2 in there, and then I jump over to still in row 2, but I'm now in the P block. Excuse me. And I have 2 electrons in there. So there's my electron configuration. My orbital diagram will only show the outermost, and anything that's the outermost is also called the valence electrons. And so for the S, I'm going to draw 1 line. For the P, I'm going to draw 3 lines. And then I'm going to use the rule, start at the lowest energy and then work up. So in the 2S, I have 1, 2, they had to be paired up. And in the 2P, I'm going to start on the left and I'm going to keep them unpaired for as long as possible. All right, so there's the orbital diagram for carbon. But what about the quantum numbers? All right, we're going to call this one A, call this one B, we're going to call this one C, we're going to call that one D. The quantum numbers, remember, is a coordinate system. And so I have to say N, which is the shell, L, which is the subshell, M sub L, which is the orbital, and M sub S, which is the spin. All right, and I'm going to do that for A, B, C, and D. All right, so let's take a look at A. Well, we know it is in shell 2. What about L? Which subshell is it? Now, keep in mind, yes, I know it's S, but there has to be a numeric value for that. So remember, S is 0, P is 1, D is 2. And then, of course, F would be 3. All right, so am I in S, am I in P, or am I in D? And I am in S, so I'm going to put 0. So I know I'm in shape S, or shape sphere. But which one? Well, there's only one, and so it gets the numeric value 0. So it's also in, and that's telling me there's only one. What are you asking me? And then the spin in this case is a positive spin. And remember, the 1/2 just represents that. So for B, it's going to be identical except the spin. So we're still in shell 2. We're still in shape 0 or S. We are still in the orbital because there's only one, but this time I have the opposite spin. All right, let's move over to C. I am still in row 2. Okay, I'm in shell 2. I am in shape P, which is 1. But which P orbital? Okay, there's an X, a Y, and a Z, but in quantum numbers, we don't use those. We give them numbers. So you start from negative, go through 0 to positive. And so I'm in which orbital? I'm in the -1 orbital, and I have a positive spin. So for D, I'm in shell 2, but I am in P, but I'm in orbital 0. That's the which orbital, that's the identity, that's the 3D coordinate, and I am still 1/2. So So that's how they all tie together. Let's do another one. Let's do iron. All right, so for iron, I'm looking at my periodic table. It is number 26. Kind of far away, but I'm pretty sure it says 26. All right. So I've got argon. That's the last one that's filled. And then I'm in row 4, shape S, and I'm going to fill it. All right. Now, I am not in row 4 anymore. Remember, the 3 Ds now come into play. So I'm still going to put the 3 because these belong to row 3. And I'm in the Ds. And I am 1, 2, 3, 4, 5, 6 places over. 6 places over. And I'm going to now do the orbital diagram. All right, now again, you only have to do the orbital diagram for anything that's passed. Now, tricky question. Which of these are valence and which of them are just past the noble gas core? Technically, those are the valence electrons because they're in the outermost shell. Normally, we don't talk about valence electrons and the transition metals, but technically that's what it would be because the valence is the outermost electrons in the outermost shell. All right, so let's draw one line for 4s, and we're going to draw 5 lines for 3d. All right, the 4s is going to be filled, and then the 3D, keep them unpaired for as long as possible. That's Hund's rule. And then I'm stuck. And by convention, we're going to go back to the left and start to fill them up. So that's 3D6. Now, can we interpret from the orbital diagram? Yes, but we're going to jump right to the quantum numbers. So what should we call them? I guess we should do them all again. A, B, C, D, E, F, G, and H. All right, so for the quantum numbers, we need to know the shell. We need to know the subshell. We need to know which orbital it is. And we need to know its spin. And so we will do A first. A is in shell 4. It is in shape 0. It is in which one? Well, there's only one, so it's 0, and it has a up spin. B is going to be identical, except the spin. C, okay, now this is in row 3. This is a 3D, so it's actually a 3, and my subshell or my shape is D, so that's a 2. Well, which one am I in? You always start from negative to positive. So that is in which orbital? It's in the negative 2 orbital. And which way is it spinning? Up spin. D is going to have the same with a different spin. E, all right, I'm still in 3. I'm still in shape D, but which one am I in? I'm in negative 1, and it's an up spin. F is 3, 2, but I'm in a different orbital, still with an up spin. E, F, G is again 3 and 2, but this time in the 1 orbital. And last but not least, we're still in 3, we're still shape D, but I'm in the 1 labeled 2. Haha, that sounded funny. And there's the quantum numbers for everything that goes in that outer past the noble gas core. All right, what is the relationship between the electron configuration, the orbital diagram, and the quantum numbers? The orbital diagram and the electron configuration come about because of the coordinate system, which is called the quantum numbers. So I'm going to once again work through the quantum numbers, and we're going to see what it is telling me. All right, so quantum numbers. N can be anything from 1 to infinity. What's that an infinity sign? L can be anything from 0 2, n minus 1. So it's telling me the possible shapes depend on which shell you're in. So you get as many shells as whatever our n is starting, but the L will be dependent on which shell that is, and you could have multiple subshells in there. M sub L, that's going to tell us which location or which 3D space. So we're going to go from a negative L through 0 to a positive L, and then M sub S is either a plus 1/2 or a minus 1/2. All right, so numerically, let's take a look at what this is saying. All right, so if n is equal to 1, and notice n cannot be 0, but you have to have the first shell. If n is equal to 1, L is equal to 0 all the way through to 1 minus 1. So basically, it is 0 to 0, which is, hey, guess what? You get 0. So this is telling us we get one subshell. We get one subshell. And so it has to take all three-dimensional space. So how many orbitals do you have to describe three-dimensional space? And that's where M sub L comes into being. That's our three-dimensional coordinate system. And it's a sphere, and so a sphere can do that just by itself. And so you get a negative L through 0 to a positive L. And again, we get 0 to 0. So there's only one of them. One orbital, and its shape, 90% of the time, the electron will be located in, remember we call this shape S, which is a sphere. Okay, well, how many spins can you have? Well, it can hold 2. One of them has to have a plus, and one of them has to have a minus. All right, let's look at n equals 2. All right, if you want to know what shapes or what subshells are in row 2, well, you're going to go from 0 to n minus 1. So I get 0 and 1. I get 0 and 1, which means there are 2 subshells. We have the S's, which are spheres, and we get the P, which are dumbbells. Okay, when you do M sub L, you have to talk about them individually. So if L is equal to 0, M sub L, well, we already saw that. It's 0 because there's only one. It's a sphere. But if L is 1, the M sub L is a negative 1, a 0, and a 1. That's telling you how many lines to draw. Okay, those are orbitals. So the lines that we use in the orbital diagram is literally the orbital. And then, of course, the spins can be plus and minus. So this would be called 2s, and this would be called 2p. And if you really want to put a number to it, it's those. It's those. All right, now why are there 3 p's and there's only 1 s? So remember, I'm trying to describe where the electron can live around the nucleus. Well, if you're a sphere, okay, so here's my nucleus. If you're a sphere, I know this is flat, but picture that a sphere, you only need 1 because a sphere will describe all three-dimensional space. But if you're a dumbbell, that will only describe 1 axis. So I'm going to have 2y, 2x, and 2z. So why do I have to have 3? Because if you want to describe three-dimensional space, you're going to need 3 of them. Y, x, and z. And then, of course, that is also surrounded by the s. Oh, okay. And then how many electrons can go in each? 2 for each one of those. So for n equals 3, you can have L 0, 2, 3 minus 1. So you get 0, 1, and 2. That is 3 subshells. You get S, you get P, and then you get D. So you've got your spheres, you've got your dumbbells, and then for most of them, these are like overleads. Okay, if you want to talk about M sub L, you're going to talk about each one of them individually. So M sub L for this one is just 0. M sub L for the 1 is a -1, 0, and 1. And M sub L for shape 2 or D's is a -2, -1, 0, 1, and 2. And that's why you draw 5 lines. All right, what is this predicting? Okay, what is this predicting? I'm going to go out of the whiteboard and I'm going to go into my wonderful little probability versus stability. And this is on Canvas here, if you find it interesting and useful. All right, so what we just did, okay, is it told us for n equals 1, you can have the shape P, or sorry, the shape S, which is numeric value 0. That's all you get. For shell 2, you can have the S, but you also get the P's. And remember, each one of them is an orbital, but it can hold 2 electrons. And then we're done. That's all you get for n equals 2. N equals 3, what are we going to add on? It's an n. We're still going to have our S's. You always start from low energy to high energy. You're going to get some more P's, but you're going to add the D's. And how many orbitals are you going to add? You get 5 orbitals that can each hold 2 electrons. And guess what? When you get to n equals 4, you get the S's, you get the P's, you get more D's. And remember, everything above it is still there. We're just expanding outwards. But I also get the S. I also get the S. Now, technically right here, I should have, let me see where we are. We should also have the G's. But we don't have any elements that use the G's. Let's see, so here's the G's. So I didn't draw them, but technically they're there and they're empty and available to be used. So we would also gain another one on n equals 5, another one on n equals 6, and even more on n equals 7. But the most that we ever see on the periodic table are the F's. All right, now, why doesn't the periodic table look like that? Because that's probability. Stability says that sometimes they're not going to quite go in the same energy order. So who is the lowest in energy? It's the S's. And then if you'll follow the periodic table, trust the periodic table, n equals 1, I'm done. You get the S's and we work to the next shell. Keep in mind, that is why hydrogen and helium are above column 1 and column 2, not because of their characteristics, but because of their electron configurations. All right, in n equals 2, we now get an additional S, and it's telling me, the periodic table is telling me, jump, and the next things you're going to fill are the 2 P's. When we get to n equals 3, you are going to fill, let me see, 1, 2, 3, we're going to fill the S's, and it's telling me jump to the 3 P's, and then I get to the n equals 4, and it tells me to, wait a second, I didn't fill the 3 D's. Okay, in probability, they're there, but actually the 4 S's are lower in energy from that diagram that I'll go back and show you in just a few minutes. So trust the periodic table. It is telling me to fill the 4 S's and then the 3 D's, and then get back to 4P. Okay, that's 3P, 2P. Oh, okay. Trust the periodic table. It's then now telling you to not worry about F's yet. It's telling you to go back and fill 5S2 trust the periodic table. This is 4 D's, and then we're back to the 5 P's. And if you'll notice, it's telling me to go clear over here to 6, fill up the 6 S's, and then that's the first time you get to see the 4 F's. And then you're going to fill the 5 D's, and then you're going to go to the 6 P's. All right, so just trust the periodic table. Trust the periodic table. Okay, that's great, but can you, draw the lines for me? Sure. This, gotta have some space here. Get rid of that top portion. This is one line called the S. And then you would put whatever number it is in front of it. These down here are the F's. 1, 2, 3, 4, 5, 6, 7. So we would call those the F's. And I'm going to put N because it will go with whatever shell you're interested in. And numerically, it would be 1, 2, 3, 4, 5, 6, 7. So you're going to go -3, -2, -1, 0, 1, 2, and 3. The D's would be 1, 2, 3, 4, and 5. So you'd say ND. But if you needed a number, it would be -2, -1, 0, 1, and 2. And for the P's, now in this case, remember, these don't live here for probability. For the P's, you would draw 3 lines. And we would call it the NP's. And we would go -1, 0, and 1. So all 3 of them go together, and it's all based on basically the quantum numbers. I'm going to go back to the notes for just a moment. There we are. And I'm going to stop and go back in just to make sure you can see it. Sometimes it doesn't jump with me. I'm going to go back up to this wonderful little picture. So what I was just showing you is the first one is the 1s. And then in row 2, you get both the S's and the P's, but the S's are lower in energy. And then you get the 3's, you get the S's again, you get the P's again. Oh, and this is why the 4 S's are actually lower in energy than 3 D's. And that's why we have to trust the stability, not the probability. All right, let's go do one example before we tie this together. All right, we are going to do sulfur, okay? What are the quantum numbers for sulfur? Well, if you want to know the quantum numbers, you have to know where we're located. So sulfur is number, it's below oxygen, and it's number 16. It's number 16. Well, what I find the easiest is just do the electron configuration. All right, so the electron configuration is going to be, who is my last noble gas? My last noble gas was neon. And then I get to 3s2, 3p, and then I'm going over 1, 2, 3, 4. Going over 4. All right, that's the electron configuration. Now let's do the orbital diagram. So there's your 3 S's. I only draw 1 line. I draw 3 lines for my P's. My S is filled, and I have 4 in the P's. So there is the orbital diagram. Now the orbital diagram will help you predict its properties. Specifically, ionic properties. So because of this, I can see that if I gain 2, I will look like the noble gas argon. And so the charge most likely is a -2. And yes,
sulfur likes to be a fixed -2. All right, well, what about my quantum numbers? Well, I already put the quantum numbers there, but if we want it in math terms, we're going to say, maybe we'll just do it this way, 3, 0, 0, plus 3, 0, 0, minus spin. 3, okay, now I'm in a different subshell, a different shape. So it's telling me it's shape P. Which P am I in? I'm in -1, and I am a plus spin. I'm still in 3, I'm still in shape P, I'm still in orbital -1, but I have an opposite spin or a negative spin. This one is 3, I'm still shape P, but I'm in orbital 0 with a positive spin. And I'm 3, 1, 1 with a positive spin. So all 3 of them go together. So if you have one, you pretty much have the others. All right, so electron configuration. It gives you, if you will, an orderly description of the electrons. Where the quantum numbers, they tell you exact location or coordinates. They each have their purpose. They each have their purpose. If I gave you n is equal to 2, L is equal to, let's say 1, M sub L is a -1, and M sub S is equal to a -1. So if those are the quantum numbers I gave you, you can actually draw the orbital diagram and the electron configuration. So I know I'm in shell 2. I know I'm in shape P. Which P am I in? I'm in -1. And which way am I spinning? Down. And by convention, you can't do the down spins until you have the up spins. So that must be 3. Oh, I put a 2 there. 2P, 2P, 3. Oh, well, who is 2P3? That is 1, 2, 3. That looks like nitrogen. So nitrogen is this. It's this. Did I count that correctly? 1, 2, 3. Oh, I didn't count it correctly. See, I need somebody here to count for me. That's 4, not 3. So that's 2P4. So I'm not nitrogen, I'm oxygen. All right, so I'm 2s2, 2p4, but I am also, let me see, what am I missing? Oh, and the orbital diagram. Those are all saying the exact same thing. They just have different purposes. All right, I hope that tied together the 3 types of descriptions. And again, rewatch whichever ones you need to, and of course, ask me questions. But until next time, jolly out.